I have the pleasure of announcing Jim Murray, who needs no introduction. Most of you, probably all of you know him. He's been here quite a while. I was going to talk about his undergrad and graduate degrees, but he said that was going to feed into his talk. So I'm going to let him do that. But he's been here a long time, and he's going to tell us about oil production, energy independence, economic growth, and climate change.
Well, we'll talk about Scylla versus Charybdis. And when Homer wrote about Odysseus's voyages, and Odysseus had to make the passageway between Sicily and the boot of Italy, Calabria, he had to make a choice, difficult choice, whether to go on the Italian side and face the rocky shores of the six-headed monster of Scalia, or go on to take a little bit longer shot on the Sicilian side, where there was a monster that was actually a whirlpool. And so if he went on the whirlpool side, he risked losing his whole boat and everybody. If he went on the Italian side, the Calabrian side, he was just a few men. So he elected to go on the Calabrian side, did lose a few men, but didn't lose his whole boat. So this idiom, it shows up in different ways. We hear about Scalia versus Charybdis, and we hear about between a rock and a hard place, and between the devil and the deep blue sea. And these idioms relate to having to make a difficult choice between two alternatives. Maybe neither one is very attractive. In the modern day, in the context of this talk, we're going to talk about this in terms of the modern day energy policy, which you can characterize as how can we abandon fossil fuels and avoid global warming, but at the same time avoid an energy economic crisis. So this, I've given several talks on this over the past 15 years periodically, and every now and then I feel like I need to update people about what the data look like, which I'll show you today. I have some background in this in a way. My undergraduate degree was in geology at Berkeley, and I graduated in '68. And my main focus was on geology of fluids, which focused a lot on petroleum geology at that time with Red Berry at Berkeley. And I more or less abandoned it. I didn't think about it much for 30 years, and it came back to my attention with a friend that I do bike riding with, and he said, "Well, you got to be concerned about peak oil." And I said, "Well, I know about peak oil. I read the papers back in the '60s." But anyway, since then, I've written 3 papers. If anybody wants more detail, I can provide you with the PowerPoint from the talk, or any one of those 3 papers that I've written in peer-reviewed journals. And a little bit of a roadmap. I'm going to give you a little background so everybody has a little the same basic knowledge about oil production, oil price, a little bit of geology, and then I'm going to talk about the production of oil, where we stand today, what it's been like in the last 20, 30, 40 years. Talk about what controls the price of oil. Talk about the role of the oil in the economy. Interaction between oil production, various economic parameters. Talk a little bit about whether America can become energy independent. And then I'll talk about the possible impacts on oil production and climate change, and say a few words at the end about the possibilities of renewable, non-fossil fuel energy sources. So, a little bit of background. It's interesting. I hope I don't have very many of these little conflicts in presentation anyway. There's a couple of things about oil production that most people are not aware of. And they're highlighted on this slide. There's two main agencies that report production of oil. One's the IEA, the International Energy Agency that's in Paris, and the other is the EIA, the Energy Information Agency, is part of the DOE in the United States. And a third institute that I'll refer to is the API, American Petroleum Institute, only because they define the density scale for how you describe oil is defined by a scale called the API scale. And it's kind of weird, so I need to just explain this. That higher API values is a lower density. Sort of an average oil density might be 45 on some arbitrary scale. And if it's 45 to 70, it's considered low density oil. High density oil, more sludgy oil, is maybe 15 to 45. So these agencies report oil in different ways, and I prefer to use what's the EIA, the Energy Information Agency definition, which reports oil as being crude oil plus condensates. And condensates, what are those? Those are low density hydrocarbon liquids. They have they're very light. API is 45 to 70. They're mostly pentane, but they can range from C5 to C9 carbon chains. The IEA, the Paris group, reports not only condensates, but natural gas liquids, which are ethane, propane, butane, which have some uses, but they're not crude oil. Biofuels, which come from corn, perhaps other grains. And processing gains, which is not oil at all. It's just the volume change. When you take oil and you process it, it increases the volume. So they call that more oil. Anyway, I prefer to make this to work in terms of what's closest to crude oil itself, which is the EIA value, which present day values are about 81 million barrels per day. The oil price doesn't apply to any of these things except crude oil only. It applies to just the crude oil that has a density of between 15 and 45. And I checked yesterday the recent prices of oil. The Brent, there's many different prices of oil. The most commonly used are one for a field in the North Sea called Brent. It's $113 a barrel in West Texas Intermediate. It's kind of amalgam for U.S. oil production. It's an artifact calculation, but it comes out to be about 110. A few more oil basics. So the source for oil in classic view is from marine, organic rich marine shale rocks. So organic rich mud was deposited in the ocean, gets scraped off, becomes rocks. It's organic rich. That's the source for oil. The oil migrates from the source rock to a reservoir rock. Reservoir rocks might be sandstone, limestone, carbonates. It migrates at slower density than water, so it'll go up the slope till it reaches a trap. In this figure, there's one example of a trap here. Is an anticline where the rocks are bent over that way, concave down, I guess. And they can't migrate any further, so that the oil is trapped. And there's other kinds of traps. There's fault traps, hydrodynamic traps. If there's gas in the system, and there is usually, the gas is lighter density than the oil, so you might have a gas layer, an oil layer, and then water. The big advent in the last 10 years, starting about 2012, was the development of fracking light tight oil. Light tight oil has taken advantage of technologies that existed previously for doing horizontal drilling and hydrofracking. And what they're doing is taking the oil out of the source rock itself, which before it migrates. So these organic rich shales have oil that hasn't migrated out, and it's still there in the porosity. Fracking is a kind of an impressive process. They can drill vertically and then they can twist the drill stem so that it drills horizontally along a layer of shale. And they go some large distances, a mile, a kilometer or so. And when after they've drilled it, what they do is they apply under high pressure water, a mixture of water and organic chemicals and sand. And the high pressure and the water fracture the shale rock that's around the well. And then the fractures are kept open by this injection of sand and chemicals. So any organic, any oil and gas that's in the shale rock can migrate out pretty rapidly to the well and then get brought to the surface and delivered. As you might imagine, this whole process is very expensive. So doing fracking is a very expensive well. One of the problems with these kinds of wells, like tight oil, is that the first year decline rates are astronomical. This particular, here's I just showed you data from one real well example from the Bakken Formation in North Dakota. And the first year decline rate for this example is 70%. So you get a large, very initial production of oil, and within a year it's down. So this has led to what's called the Red Queen effect. This comes out of the Lewis Carroll through the looking glass, where the Red Queen has to run faster and faster just to stay in place. And basically you have to drill more and more wells, not only to keep production constant, but to increase production. So I've got one numerical example here. If you want to produce 1 million barrels per day, a conventional oil field might require 60 new wells per year. And a light tight oil field might require 2,500 new wells. So not only is it expensive, you've got to drill lots of wells. So conventional oil, source rocks, organic, marine shells, oil migrates to reservoir rocks, decline rates about 5% per year. Light tight oil, source rocks, same source rocks, but you produce the oil from the source rocks by fracking. It's very expensive. Decline rates are 50% per year. And as a result of this advent of the light tight oil production, the companies involved in producing light tight oil historically lost money. None of them were profitable until just the last year or so. And I understand why, and it's understood why, but I'm not going to take the time to explain it to you now. But it seems very odd that they'd be producing light tight oil if they're losing money. Finally, the investors got tired of investing in companies that were losing money. So they demanded that the companies improve their bottom line. And so they've done that. So the losses have been modulated. They've done that by decreasing investment in more wells. So the bottom line is improved. Companies are now, some of the companies are making money, not all of them. But it also makes the increase in future production less likely, because I pointed out to you already that because of the drilling treadmill, you need more and more wells. You can't just cut back on the wells and expect to get the same amount of production. So shale is a source rock, and it's not, if companies had any alternative, they would go for conventional oil. It's a simple well, you drill it down, the oil flows out. They're only doing this light tight oil because the conventional opportunities are exhausted, or they're marginal. And because the price of oil climbed to support the more expensive cost of production. And it didn't even totally cover that, because I pointed out companies were losing money. So the first point or question I want to address is, can we increase oil production? So what I've got here is a plot of oil production on the y-axis versus years. This starts about 2000. Can you guys see my red dot? I can use it.
Yeah.
Okay. 2000 to 21, 2021, 2022. And it shows oil production by country. They're color coded. So you can see, maybe you can see that the US is the largest producer, followed by Russia, Saudi Arabia, Canada, and Iraq. Those are the largest producers of oil. And the point I wanted to make about this graph is that for the last 20 years, since about 2004, with the exception of an increase in production in the United States, global oil production has been dead constant. It hasn't changed one iota. And the only reason why production in the United States has increased is because of the fracking of light tight oil. So another way you can characterize this is you can say that the only reason there's been any increase in global oil production is because of the production of light tight oil in the US. Let me see a couple of more slides about that. This is the same data replotted as conventional oil, which you can see wiggles around, but fundamentally it's been constant since about 2004. Deep water oil and oil sands. Deep water is mostly the Gulf of Mexico production, and oil sands mostly Alberta. Alberta's production has historically been about 1 million barrels per day. It's increased over the last few years, maybe 2, last decade, maybe to 2. But the big increase in global oil production has been in the tight oil, the light tight oil in the United States. And I didn't point out in this slide and the last slide, there was a big crash in production that was due to the COVID recession. But at least on this plot and the previous one, the maximum in tight oil production occurred about to 2019. Here's another way to look at it. If I said the light tight oil production was in the US, we can just look at the US production by itself. Conventional oil is in the green. Oh, this is a plot that goes back, I can't read it myself, but it might be 1940, I don't know, to about the present. And you can see the conventional oil peaked around 1970. And this was the classic prediction by M. King Hubbard that the US would have peak oil about 1970. He made that prediction in the mid-50s when US oil production was increasing systematically. And he was fundamentally right. I mean, what he didn't know about, and you can't blame him for an error in his prediction, is that there'd be an increase in offshore Gulf of Mexico production, which is now in decline, and Alaskan oil production, Prudhoe Bay, which is also in decline. So overall, US oil production did reach a maximum around about 1970. And about 2012, there was this big increase in tight oil production, which increased to a maximum in 2019, and it's been decreasing in the last couple of years. So I think you can make a case that if the tight oil production is falling, the world may be close to the all-time peak of world oil production. I guess time will tell. And I feel that this tight oil increment will be short-lived. And if it's short-lived and it decreases rapidly because of the rapid decline rates of those wells, and the fact that the hotspots have been drilled first, the areas left to be drilled are not as productive. That the prospects for crude oil condensate production to exceed 73 are not very good, 73 million barrels per day. So that was the value that I had the dotted line on here, 73. So that's one part of my fundamental argument. So briefly, we can look at this question: can we make the US energy independent? And we hear that a lot from politicians and pundits. And so let's look at the data. This is a plot of oil production on the y-axis versus time going back to 1950. And the blue is US consumption. The brown is US production. You can see the increase here about 2012 due to the light tight oil production. The imports are in green. The exports are in yellow. And the net imports, the difference between imports and exports is this red line. And the zero is that line that's above the baseline. So I circled this last little point because it went negative. So in terms of the current numbers, or maybe last year's numbers, the US produced 84 million barrels per day, consumes 18.1, it exports 8.5, yet it imports 8.0. So the question is, why is the US exporting so much oil that we have to import oil? If you look at the difference between the import and the export, you can see that the US is this year, it's become suddenly a net exporter. That's this little tick here. To many places, but especially to Canada. This is a side note, but Canada, which produces this sludge from tar sands, oil sands, that sludge can't go through pipelines like the XL pipeline, which has been controversial. So what they do is they import the low density light tight oil and mix it with their high density sludge from the tar sands, oil sands, to make a mixture that can be pumped down the pipeline. So that's why Canada is a major importer of light tight oil. But furthermore, there's more light tight oil exported. Why aren't we using it if we're producing it? Why are we importing oil? And the reason why is because the refineries in the US are fundamentally not set up to refine low density oil of this type. It's light tight oil that has the API of 45 to 70. You might think, well, it should be an easy thing to convert to refineries, but it's not. It's kind of a big process. And so rather than try to modify the refineries to refine this light tight oil, they export it. So it's kind of a mess. You might wonder, well, what controls the long-term price of oil? And this has become a big issue. I showed you that the price of oil at Brent and West Texas Intermediate was 110 or 113. That's reflected by that ends up being reflected by the cost of gasoline. And everybody's complaining about the cost of gasoline now. It's at least $4 a gallon, and some places $6. So what controls the long-term price of oil? And in the long term, it's controlled by like a lot of things that we talked about in oceanography, it's controlled by the balance between supply and demand, the international supply and demand. And when there's an oversupply, the price goes down, and an undersupply, the price goes up. You think after monitoring or manufacturing this resource for so long, we kind of get it so it's pretty smooth and constant, but it fluctuates a lot. And here's an example of some data. This is the Brent price in sort of yellow. The bottom bars down here show the balance. When there's a negative balance, a deficiency in supply, the price goes up. When there's a abundance of supply, blue, price goes down. That's the long-term price. The long-term price is controlled by simple mass balance. And the short term, other factors get involved. So when we're seeing effects like unanticipated expectations. So the COVID recession or the supply chain problems, they cause the price to go up. Things like bad luck, Hurricane Ida would close up some of the refineries in St. Charles, Louisiana. Bad decisions. Germany voted out nuclear power without making any allowances for replacing that energy with other fossil fuels. presidents are getting a lot of heat about the price of oil, most recently, especially Biden. But we can realize that Obama, for example, was president during the largest expansion of oil production in US history. And he just happened to be president when fracking took off. So he had nothing to do with it. It wasn't his responsibility, but it happened during his presidency. And Biden had the unfortunate occurrence of the Great Recession, or not the Great Recession, the COVID recession. But during the Biden administration, the increase in drilling of about 63%. So it's hard to blame Biden for the price of oil on the short term. So fundamentally, the presidents, whether it's Obama, Trump, or Biden, none of them have any influence really on the price of oil. Okay, energy is the economy. And the question is, can we have global economic growth with no growth in energy? So this first plot is a plot of GDP for different countries versus their oil consumption on the x-axis and the GDP. This is a log plot, so it takes out some of the scatter, but it's got all the countries of the world. You can see the US and China are up here on the top right. They have the largest oil consumption, the largest GDP. Other countries fall down along the slope. If you did it on a linear plot, it would still be somewhat similar, although most of these countries would be down here in a group circle in the very lower left-hand corner. The US and China would be way off up to the upper right by themselves. So it means there's some fundamental relationship between oil consumption and GDP. And if the IEA has argued that there's a net zero roadmap, it's going to lead to an 80% reduction in oil consumption by 2050. We have to assume that that's going to have a big impact on GDP, gross domestic product. Energy is a fundamental process influencing inflation. Inflation is all in the news now. So this is a plot of the last 30 years or so of inflation in the blue line and price of oil. In this case, it's West Texas Intermediate, yellow line. And you can see there's a really good correlation when the price of oil goes up, inflation goes up. Current values of inflation, which are actually coming down in the last month or so, have been about 7.98%. Of course, reflecting the big increase in the price of oil, which has gone up to over $100 a barrel. What economists do to take out this exaggerated effect of the cost of oil is they report an inflation value that's got the core, what they call the core components, or without oil, without the price of oil, and without the price of food. So it's kind of reflects the inflation, changing the price for everything else. And that value was just reported yesterday or today. It's about 4.9%. So there's still a lot of, you take out the cost of oil, the direct cost of oil on inflation, you still have a lot of inflation. But the price of oil can still influence that inflation as well, because oil is used for all kinds of things like transportation and making plastics. There's secondary uses for oil that would not be reflected by just removing the price of oil by itself. So the price of oil influences inflation in lots of different ways. And the last slide in this little group is that pointing out these are showing price on the kind of a normalized price versus years. And these gray bars, which I hope you could see, are when there was recessions. And maybe you can kind of see if you squint But each one, or the main point of this graph is that energy price spikes have preceded every recession for the last 80 years. So you guess you could have the expectation that if our price spike continues, current price spike continues, we're going to be headed for a recession. So oil plays a major role in the economy. And we're now experiencing what energy folks call the fourth oil shock. This first one is the Iraq. No, the first one was the Yom Kippur War. First one, I think, Yom Kippur War, 1973. I remember driving back from graduate school in 73 and having to go with a speed limit of 60 across the country. And it was very calming, but it took a long time. It's amazing how much less oil how much gasoline I use. And as an aside, I'll just raise a little comment, personal comment, that when you hear everybody complain about the price of oil, price of gasoline, I wonder just how many of them have cut down their speed limit a little bit. I don't think anybody's driving any slower than they did before. Anyway, 1980, the Iran Revolution. Come back here. The rise of China in 2008. That was the 2007, 2008 price spike. And then this current oil shock, which is still underway, and we have to see how it's going to play out. Because it's largely due to the removal of Russian crude oil from the market, which was predicted. A lot of times the financial markets will respond to predictions rather than the real cases, real data. But so far, my understanding is that there's been not a large reduction in the export of Russian oil. They've managed to, the United States has said they're not going to import Russian oil, and maybe Europe is doing some. I'm not sure how extensive the European Union is doing. But apparently Russia's finding a way to sell their oil to other countries and not doing the embargo, which is kind of what I anticipated might happen. But Daniel Yergin, who also I don't always agree with in his statements, but has made a recent statement that this is one of the possibly historic moments in world energy, and that world energy and economic systems are in a fragile state. We'll just have to see how they evolve here in the next year. So this is a seminar I like to give to the program on climate change, because I'd like to address how this might relate to uncertainty in climate change. And typically, when we talk about uncertainty in climate change, you go to seminars, PCC seminars, and somebody will talk about the effect of cloud cover, or the effect of ice in the Arctic, or impacts, variability and impacts of increasing CO2, global warming. But virtually nobody, except me occasionally, talk about the uncertainty expressed in terms of CO2 production. And I think there's a good case that we should pay more attention to this. And I'm going to show you my arguments. There's been a little bit of history on how this has been done by the IPCC. In 2000, they produced what are called the SRES scenarios. These were 4 families of scenarios, A1, A2, B1, B2, that were developed. There were 40 scenarios. These different families take into account different amounts of global versus regional factors, environmental versus economic. And they've been replaced now, so I don't need to go through the details. But basically, they made predictions of how the atmospheric CO2 was going to increase by making different assumptions about how fossil fuels were going to be produced or consumed. Those SRES were replaced in the AR5, the fifth assessment report 2014, by what are called representative concentration pathways. And in those pathways, the IPCC deemed it best to report how much warming was going to occur in terms of watts per square meter. And use those because those were the more direct input into the models that were being used to predict future climate change. But those are, in fact, had to be driven by some increases in CO2 due to fossil fuel burning. The SRES, resource availability, that means oil, coal, and natural gas, were put together by these energy economists led by especially a paper by Rogner in 1997, and a follow-up by Gregory Rogner in 98. And these energy economists are at the International Institute for Applied System Analysis. It's in Vienna. Well, these guys make their predictions and make these comments. Rogner, his message was that there's vast unconventional hydrocarbon occurrences, and technology is going to change. He didn't know what it was going to be, but he just said it's going to change, and it's going to allow hundreds of years of availability of fossil fuel with long, low-term costs. So they didn't try to take into account any cost impact on consumption of fossil fuels. By long, low term, he meant the costs that were available when this report was written. 97 was probably written a year or two before that. In the 90s, the price of oil was about $40 a barrel for an extended period. So they were assuming it was basically going to change. They weren't considering $100 or more cost of oil, barrel of oil. And then Adelman and Lynch, along the same vein, they stated that claims of unlimited volumes of recoverable oil, they call those doomsday scenarios, were basically, there's huge amounts of hydrocarbons. The technology is going to change and improve their take advantage of those technology advances to produce those hydrocarbons. And their hope was things like methane hydrates would be found to be produced, things like that. So they had no consideration, no realization that maybe there's going to be constant production or declining production. So there's my data that I showed you, and you can see that oil production, except for the fracking, has been constant since 2004. So I wrote a paper in 2016, and I put together how this might look. It turned out to be, I made a plot of oil consumption versus years. This is 2000 to 2100. The RCPs were talked about oil consumption in terms of ettajoules per year energy. There's a conversion from ettajoules to barrels of oil. So I did a scale on the right-hand side is gigabarrels per year of how much oil was expected to be produced for these different RCP values. Now I have to tell you that it was extremely difficult to find these values, and I could not get a direct answer from any of the authors of the RCP. It would not be forthcoming about how much oil they predicted. But I did find one figure. I bet it was a mistake that he published it. This paper by Van Buren, 2011, where I was able to glean the scenario they envisioned for oil production to make a comparison with the data that I showed. So that's where I got these numbers. So you can see that the fact on the scale of 2000 to 2100, we're already at 2022. We're almost at 2025 here. So we've moved along the scale quite a bit already. To calculate the warming anticipated for RCP 8.5, the global consumption of oil would have to increase from about 28 gigabarrels to 78. It's almost essentially doubling. To generate the 8.5, RCP 8.5, you've got to have oil doubling over the next 50 years. To generate the 6.0 watts per square meter, it starts off low, but it continues to increase over the whole century. Again, not doubling, but increasing by about 30%. The only two that I might say might be plausible are the RCP 4.5, where it stays more or less constant over the rest of the century, and 2.6, where they actually envision it decreasing significantly. So a lot of us would like to think, and that includes me, that, well, I'm talking just about fossil fuels here, maybe the hero is going to be renewable resources, non-fossil fuel energy. And I would hope that's the case, but there's some problems. The first is its contribution right now, and I call this the timing. This is a plot that starts at 1900 to the present, and it shows the historical use of coal, oil, natural gas, non-fossil energy, which is hydroelectric and nuclear.
Is that global or for the US?
This is global. And population change. So you can see there's the total energy use is correlated really strongly with population change, which more people want to use more energy, or we use the same amount of energy, it's going to increase. Renewables, this plot is a year old, maybe 2 years old. This plot was made, renewables were 4%. They might be a little, they might be higher. They are higher now, maybe 6%. I forgot to check exactly. But the problem is the timing. There's two aspects of the timing. The one is we're talking about renewables replacing fossil fuels. And I have to point out over the history of the evolution of fossil fuel use, new sources of fossil fuel have grown, but they've never replaced the previous one. They just added on to the other one. So coal has continued. Oil didn't replace the coal. It just tacked onto the top of it. Natural gas, so on. So it's hard to envision an increase in renewables to replace this amount of fossil fuel use. And the timing issue has to do with the amount of carbon you can burn without risking catastrophic warming. And I have a reference there, but my IPCC prediction was we had to do something within almost 10 years in order to avoid catastrophic warming. And I think there's few credible energy analysis that believe you can fully replace fossil fuels that soon. Another aspect of this is global emissions and where they come from. I like to get an electric car. A lot of my colleagues have electric cars. Looking at maybe getting a Tesla. But all of our focus on making electric cars are only 15% of the total global emissions. And even for internal combustion energies, globally, there's 165 million internal combustion energies, and less than 50% of those are for cars. There's trucks that burn diesel, and there's aviation and shipping. And then the rest of the fossil fuel production, CO2 emissions are from energy industry. There's 1.6 billion cars on the earth, and less than 1% of them are electric. And gosh, I'd like to see more of them be electric, and they're certainly increasing rapidly, but I can't take a realistic view that that's going to change in a timely way. So kind of in conclusion, I say we got a tough choice. We can steer towards the rocky shore, reduce skyline, limit oil production to minimize global warming at the possible prospect of driving the price of oil up, which will increase inflation and increase the prospect of recessions, greatly damage the economy. Or go for Charybdis, don't limit oil production, in which case we'll certainly have global warming. And I don't know how economic growth is going to, it's hard to say that economic growth would go up because of the impacts of global warming. So I just put an arrow on there, horizontal arrow. So I'm sorry, I kind of have a negative view of things today. But I think there may be no choice. We may have no control, and geology may be in control. And if oil production won't grow to match the IPCC projections, maybe that's a good thing. It may be a solution to global warming. But lower total energy consumption is going to lead to lower or negative economic growth. And that's going to result in a significant reduction in living standards, unless we really make a massive change. I guess you could say the vision could be there if we undergo massive conservation, use available fossil fuels to build low energy infrastructures, do massive investment in renewables. But so far, those aren't really happening. So but anyway, that's my view. Maybe you've got a more positive, uplifting view. Thank you.